This is a basic module which will introduce you to some of the laws of radiation and the remarkable ways in which radiation reveals the mysteries of the universe. So these are the contents of the module. Throughout this presentation, we'll delve into several key areas. Firstly, introduction to radiation. We will start by discussing the basic concepts of radiation and its significance in astronomy. Second, black body radiation. We will explore the theory behind black body radiation and its crucial role in understanding stellar properties and the history of our universe. Third, photometry. This technique measures the light from stars and other celestial bodies, helping us infer their brightness, temperature, and vital characteristics. Fourth is spectroscopy. And fifth is some additional applications and some future research. So, radiation consists of various forms of electromagnetic waves. It is a cornerstone of modern astronomy, and it provides us with the tools to explore and understand various intrinsic properties of celestial objects like composition, temperature, distance, motion, etc. Thus, the electromagnetic spectrum, which includes everything from low energy radio waves to high energy gamma rays, serves as a window into the cosmos. This image here represents the electromagnetic spectrum and shows the scale of different waves in this electromagnetic spectrum. Next up, we'll learn about a few terms important in radiation. And Yash Palve would present a screen and derive some of them figuratively or diagrammatically. Yeah.
Hello, am I audible?
Yes.
Is my screen visible?
Yes.
Okay, so luminosity is the basic definition, which is the rate at which energy is emitted. Now, this next definition is flux. So, flux is just the amount of light received per unit area. So, what we need to do is divide luminosity by area. So, it's quite easy. Just get a point and consider a sphere around it. If the radius is r, then the surface area is 4 pi r square. So you divide luminosity by 4 pi r square and you have your flux. Next is flux density, which is nothing but its definition where you divide it by the frequency range. This is useful to have different, because flux is different at different frequencies. This is useful to formulate different stuff. Next is power. Now, the power that a telescope collects is just the flux into the area of the telescope. Since the flux is L upon 4 pi d square, as we just saw, you just multiply it with the effective area. Now, the effective area is the area with which the telescope gathers its light. For example, you have 6-inch diameter telescopes, 8-inch diameter, etc. Next is intensity. So, as defined here, intensity is flux density per unit solid angle. So, as we saw, flux density is F by delta mu, and you have to divide it by solid angle. So flux is L by 4 pi r square. D square root. Uh, Solid angle, you must remember from Gauss's law during your JE prep. If someone doesn't remember, it's basically if you have a point and you have a certain area. Now, each area is at a particular distance from the point, let's say R. So, what you have to do is this is the differential relation for a certain differential area. and you integrate it over the whole area, and you'll find the solid angle subtended by this area. This is basically the concept of angle which is used in two-dimensional applied to three dimensions. That's it. Pass on to Amit, the next part.
Yes. So now we'll be learning a bit more about black body radiation. Yeah. So at the end of 19th century, scientists encountered a perplexing problem known as the ultraviolet catastrophe. According to classical blackbody radiation theory, hot objects should emit infinite energy at short wavelengths, which contradicts the principle of energy conservation, obviously. The Rayleigh-Jeans law is an approximation to the blackbody radiation through classical arguments, which fail to solve this issue. But what exactly is blackbody radiation? A blackbody is an idealized object that absorbs all the incident radiation and re-emits it perfectly, with a characteristic spectrum that depends solely on its temperature. The radiation emitted spans a range of wavelengths from the infrared to ultraviolet, with a peak wavelength that shifts according to the Wien's law. The hotter the object, the shorter the peak wavelength. This can be clearly seen from this image. As you can see, shorter wavelengths have got a higher temperature. So Wien's law is an approximation to explain black body radiation and accurately describes it for higher frequencies or shorter wavelengths. Wien derived his law from thermodynamics arguments and using Maxwell-Boltzmann distribution for atoms. Enter Max Planck, a physicist whose work would forever change the landscape of science. Planck proposed that instead of emitting energy continuously, atoms and molecules could only emit energy in discrete amounts or quanta. This groundbreaking idea allowed Planck to formulate what we now know as Planck's law. His function accurately described the spectral distribution of radiation from a black body, or an idealized perfect emitter at various temperatures. Planck's insight into quantized energy levels not only resolved the ultraviolet catastrophe, but also laid the foundations of quantum theory. His work also earned him the Nobel Prize in 1918. So the total energy emitted by a black body per unit area is given by the Stephen-Boltzmann law, which states that this energy is proportional to its temperature raised to the fourth power. This relationship is fundamental in determining the luminosity and temperature of stars and other celestial bodies. This is one of the important applications of the black body radiation, CMBR, or cosmic microwave background radiation. Discovered by Penzias and Wilson in 1965, CMBR provides a snapshot of the entire cosmos approximately 300,000 years after the Big Bang. Kobe satellite measurements showed CMBR fits a blackbody curve at exactly 2.725 Kelvin, indicating that the universe has undergone expansion and cooling from 13.7 billion years. WMAP later revealed early temperature fluctuations as well. In summary, blackbody radiation is a crucial concept in astrophysics, helping us to understand the thermal properties and energy emissions of celestial bodies. It also plays an important role in unraveling the history and evolution of the universe itself. This image shows a nice timeline of workings on CMBR. So next up is photometry. Photometry is a crucial technique in astronomy that involves measuring the light intensity from celestial objects. By analyzing the light emitted or reflected by these objects, astronomers can infer a lot of information about their properties. So photometry quantifies the flux of the light. This measurement helps us determine the brightness of stars, galaxies, and etc. other cosmic phenomena. To obtain precise measurements, astronomers use photometric filters that isolate a specific wavelength range of light. These filters allow the study of objects in different parts of the electromagnetic spectrum. Common filter sets include UV-RIZ for ultraviolet to near infrared and JHK for studying cooler objects in the near infrared region. Here's a nice image showing the passbands of UV-RIZ and JHK filters. So everyone attentive till now in the meeting, here's a nice question for you to try, and you can raise your hand or type in the chat that you are attempting the question or like that. We are later going to give a solution of this question also. So you can take 2 to 3 minutes for trying this question if you want.
A
This
small
question is
incentive.
totally,
Whoever solves
yeah,
this first gets a treat from Anvit.
okay, sure. In aromas, sure.
And 36.7 Kelvin is wrong, unfortunately. Okay. Yeah, approximately 2 it is correct. Should we
Okay.
wait one more minute for others to solve or
Yeah, we can wait. Yes. By the way, what's the name of the person who answered the correct?
Rohan Joshi?
Okay.
DM Anvit if you want to redeem your treat.
Yeah, sure.
I think I should solve now. Is anyone still solving? Okay, fine, I'll solve. Can you see my screen?
Yes.
Okay. So to solve this question, you just need to understand the concept of energy. Whatever heat the earth is absorbing that is radiated by the sun, it should emit itself. So to find out the heat absorbed by the earth from the sun, what we do is, as we saw earlier, Ls upon 4 pi d square is just the flux, and you multiply it with pi r e square, not 4 pi r e square, because pi r square is the projection of that area, which will basically get the which will absorb the energy. Now, this is the luminosity of Earth. So, does everyone understand how we got this? So, just canceling out the terms now, and we get therefore. Now, substituting in the values, we'll get the temperature of Earth to be 278. Okay. Does anyone have any doubts? Very easy. Okay, I guess no. Sure. Let's move on.
All right. So this was a nice, easy numerical question on radiation. Uh, Side note, some of the questions that we'll be including in the assignments will be a bit more tougher, similar to like JE Advanced. So this was a really simple numerical question, but if you really want a challenge, then you can solve the assignments. Now we'll be learning a bit more about the magnitude systems. So the magnitude system is a logarithmic scale used to quantify the brightness of astronomical objects. First is apparent magnitude. The apparent magnitude of a star is a measure of its brightness as seen from Earth. The scale is logarithmic and backwards, which means with a negative sign, meaning larger magnitudes correspond to fainter stars. For example, a star with an apparent magnitude 1 greater than than another would mean that the star is 2.5 times fainter than the before. Next is absolute magnitude. It is a measure of the intrinsic brightness of a star defined as the apparent magnitude if it were located at a distance of 10 parsecs away from Earth. So you can consider a star to be at roughly 32.6 light years away from Earth, and what its apparent magnitude would be. This is the absolute magnitude. Here are a few equations which Yash will further derive if you want. Yeah.
Yeah. Okay. So, we'll first write our basic formula down. Now, as we saw in the earlier definitions, flux is inversely proportional to d square. Therefore, brightness is inversely proportional to d square. So, brightness at 10 parsec on brightness at a certain distance d follows this relationship. Okay, simple enough. Now, want to find out absolute magnitude in relation to apparent magnitude. So, using the first formula, simple algebra, that's it. Does anyone have any doubts in this? Okay, fine.
Yes, I don't think so. So the next thing that we are going to learn is spectroscopy, one really important, fascinating and crucial field in radiation and one of the applications of it in astronomy. So it is a technique that studies the interaction between matter and electromagnetic radiation. In astronomy, it involves analyzing the light from celestial objects to determine their properties. This is in fact a bit different from photometry because that also analyzes light, but it mainly deals with light flux. Here we are dealing with the spectrum. Spectroscopy works by examining the wavelengths of light that atoms and molecules emit or absorb during specific energy transitions. This method allows astronomers to determine the composition, temperature, density, velocity of celestial objects and many other intrinsic properties in fact. These emission and absorption lines serve as distinctive signatures indicative of physical conditions and chemical compositions of stars, galaxies, and other astronomical phenomena. So you can have a look at this page for a while, and here are two graphs indicating a continuous spectrum and emission spectrum. Next up is Doppler effect in light. The Doppler shift is the change in wavelength or frequency of light from a source moving relative to an observer. This is in fact really similar to the Doppler shift in sound, which you might have learned in school. If a light source moves towards an observer, its wavelength appears shorter or blue shifted, similar to sound or other waves, mechanical waves. If it moves away, the wavelength appears longer or red shifted. This effect is crucial in measuring the velocities of astronomical objects. By measuring the Doppler shift of spectral lines, astronomers can determine the radial velocity of stars and galaxies, that is, their speed towards or away from us. The tangential component of this velocity has no effect in the Doppler shift. Only the radial component is what matters to us. By using Hubble's law, we can also measure the distance to that object. The velocity and distance have a linear relationship, where the constant of proportionality is the Hubble's constant. Next up is spectral broadening. Spectral lines can appear broadened due to several physical effects, each providing insight into the conditions of emitting or the absorbing material. First is intrinsic broadening. Due to the Heisenberg's uncertainty principle, the finite lifetime of excited states causes an intrinsic uncertainty in the energy levels, leading to the broadening. Next is thermal broadening. Caused by the thermal motion of atoms or molecules, the higher the temperature, the faster the particles move, leading to a broader spectrum. Next is rotational broadening. In rotating stars, the Doppler effect causes the light from the approaching limb to appear blue shifted and the light from the receding limb to appear red shifted, broadening the spectral lines. Finally, collisional broadening, also known as pressure broadening, occurs when particles are close enough that their interactions affect the energy levels, causing the lines to be spread out. Here's a nice graph indicating all the different types of broadening. You can have a look at it. Over to Yash to explain about important spectral lines now and further future endeavors in the research of radiation and its use in astrophysics.
अन्वित तूच present कर.
Alright, so I'll be the one who's presenting. Just a second. Yes. Hopefully my screen is visible.
Okay. Yeah. So the H alpha line is a line with wavelength 656 nanometers. Anvit mic बंद कर echo.
Yes, just a second.
H alpha line is a line with wavelength 656 nanometers, and it is a part of the Balmer series of hydrogen atom with transition from the third to the second energy level. The use of this emission line is so that because we know its exact wavelength, we can measure the observed wavelength and hence figure out various properties about the source of the light. Next up is 21 centimeter line. The 21 centimeter line refers to the electromagnetic radiation emitted by neutral hydrogen atoms in space at a wavelength of 21 centimeters. The transition involves the flip of the electron spin relative to the proton spin, releasing a photon in the process. I'm sure you have learned about parallel and anti-parallel electrons during your chemistry while studying for JE. So, spin or angular momentum is an intrinsic property of electrons and protons. In the ground state, if the spin of the electron and protons are aligned in the same direction, then they are said to be aligned parallelly. And if they are oriented in opposite directions, they are said to be in anti-parallel. The anti-parallel configuration is slightly lower in energy. When the electron in an hydrogen atom flips from parallel to anti-parallel, it releases some energy in the form of a photon, which has a wavelength of 21 centimeters. The 21 centimeter line is a crucial tool for mapping the distribution and density of neutral hydrogen in the interstellar medium. Because it is a radio wave, it can penetrate dust clouds that obscure visible light, allowing astronomers to see regions of space that are otherwise hidden. The Doppler shift of the 21 centimeter line allows astronomers to measure the velocity of hydrogen clouds, providing insights into the dynamics and rotation curves of galaxies. Next slide. Okay. So, starting with gamma ray bursts. Gamma ray bursts are the most energetic explosions in the universe, capable of releasing more energy in a few seconds than our sun will emit in its entire lifetime. Research focuses on understanding their origins, which are thought to include the collapse of massive stars or mergers of neutron stars. Future directions involve more detailed observations with space telescopes like the Swift and Fermi satellites and the upcoming Cherenkov telescope array. Cosmic, array, cosmic rays are high energy particles, primarily protons, that travel through space at nearly the speed of light. They originate from supernovae, active galactic nuclei, and other high energy processes. Research includes understanding their acceleration mechanisms and their impact on the interstellar medium and planetary atmospheres. Advanced detectors like the Pierre Auger Observatory and IceCube are key tools in this research. Next one. Neutrinos are nearly massless particles that rarely interact with matter, making them challenging to detect but invaluable for studying astrophysical processes. They provide unique information about phenomena such as supernovae, black holes, and the sun's core. Neutrino observatories like IceCube at the South Pole and the upcoming KM3 net in the Mediterranean Sea are leading this field. The study of exoplanets, planets orbiting stars outside our solar system, has rapidly advanced with over 5,000 exoplanets today. Key research areas include discovering new exoplanets, understanding their atmospheres, and assessing their potential habitability. This research could answer fundamental questions about the potential for life beyond Earth and the diversity of planetary systems. Next slide. Magnetohydrodynamics studies the dynamics of electrically conducting fluids like plasmas, which are found in stars, accretion disks, and planetary magnetospheres. Understanding MHD is crucial for explaining solar flares, cosmic jets, and the behavior of astrophysical plasmas. Future research involves more sophisticated simulations and observations to better understand magnetic fields' roles in various astrophysical processes, which is still not yet well understood. Next are some technological advancements. Technological advancements are the backbone of processes in astrophysics. Future telescopes and detectors, such as the Extremely Large Telescope and the Square Kilometer Array, will provide unprecedented resolution and sensitivity. Collaboration across disciplines and continuous innovation will drive the next wave of discoveries. This is an exciting time to be involved in astrophysics with many opportunities to contribute to groundbreaking discoveries. Thank you for your attention, and I look forward to answering any questions that you might have. Mm, Does anyone have any questions?
If
Because
any
who should,
part of the presentation was ambiguous or you couldn't understand, you may unmute and or even type in the chat and ask. If not, we will definitely share the slides uh, on MS Teams, and you can have a look at it and ask us if you have any doubts.
make sure you do ask them if you have any, because I don't think the assignment questions will be easy.